Picture this. You're standing in a steel box, suspended 60 stories above the pavement. The doors slide shut with a soft thud. You press the button for the lobby. And as the car begins its descent, you feel that slight, stomach-flipping lurch of gravity. Then you hear it, a loud, metallic snap. In your mind, the cables have frayed, the winch has failed. You imagine the car accelerating into a terrifying, weightless plummet toward the basement. It's the ultimate urban nightmare, the free fall. But here's the surprising truth. In the entire history of modern traction elevators, a true free fall caused by snapped cables is almost physically impossible. You aren't just riding in a dangling box, you are riding inside a high-speed mechanical interlocking fortress. Today, we are dismantling the myth of the plummeting elevator by exposing the hidden engineering friction that keeps you suspended, even when the power goes out. To understand why elevators are so incredibly safe today, we first have to travel back to the dark ages of the vertical world before the mid-1800s. Elevators did exist, but they were strictly for cargo. Humans refused to ride them, and for a very good reason. If the single hemp rope snapped, the platform became a high-speed projectile heading straight for the floor. There was no backup. It was a one-shot system. Everything changed in 1853 at the New York World's Fair. A man named Alish Otis, a showman and an inventor, stood on a platform high above a gasping crowd. He ordered an assistant to take an axe and cut the only rope holding him up. The crowd screamed, the platform dropped exactly to inches and then stopped dead. Otis famously tipped his top hat to the stunned audience and declared, "All safe. Gentlemen, all safe." He hadn't just invented a brake, he had invented the modern skyscraper. Without that single moment of engineering theater, our cities would still be flat. So what makes today's elevators so different? It all comes down to multiple layers of redundant safety systems. Starting with the mechanical brain of the operation, the governor. The first line of defense isn't a computer, it's pure physics. At the very top of the elevator shaft, separate from the main motor, sits this device called a governor. Think of it like a mechanical speed limit for gravity. The governor is a weighted flyball system connected to the elevator car by its own separate steel cable. As the elevator moves up and down at its normal speed, the governor just spins along calmly. But if the elevator begins to move too fast, say, due to a motor failure or some other anomaly, the centrifugal force causes the governor's weighted arms to fly outward. When they reach a preset critical speed, they trip a mechanical switch. There's no software, no complex sensors, no electricity required for this to happen. It's a purely mechanical if-then statement. Written in solid steel, it's simple, it's reliable, and it's always watching. Once the governor trips, it triggers the second line of defense, the safeties. These are the real teeth of the system. Located underneath the elevator car are massive, spring-loaded steel wedges. Now, to understand how these work, imagine you're sliding down a metal handrail and you suddenly decide to stop. You wouldn't just press against it, you'd need to grip it hard. That's what the safeties do. When the governor triggers them, they slam outward into the vertical guide rails that run the entire length of the shaft. These wedges are designed to literally bite into the steel rails with thousands of pounds of pressure. The more the car tries to fall, the deeper the wedges dig in, generating immense friction. It is a brilliant piece of engineering where the force of the fall itself is used to stop the fall. Through sheer mechanical friction, the elevator transforms from a falling object back into a structural part of the building. In most cases, the car stops so abruptly that the biggest danger isn't the fall, it's the sudden stop, which can feel like a minor fender bender. Now, let's talk about the myth that starts this whole nightmare. The snapped cable. The image of frayed ropes giving way is a staple of Hollywood action movies, but in reality, it's a statistical miracle. Modern elevators aren't suspended by a single rope. They hang from a bundle of between 4 and 8 high-strength steel cables. And here is the secret that filmmakers conveniently ignore. Each individual cable is strong enough to hold the weight of the entire elevator car, plus a full load of passengers, all on its own. To actually snap an elevator into a free fall, you would have to simultaneously and instantly shear through all of those independent steel ropes. The chances of that happening are practically zero, even if, somehow, This impossible event occurred, there's yet another safety system, the electromagnetic brakes on. The main motor are designed in a fail-safe state. This means the brakes are always on by default. It takes a constant flow of electricity to hold the brake pads open and allow the car to move the very moment the power cuts out or a control system detects that a cable has gone slack. The power to the brakes is cut and they clamp shut instantly, grabbing the main drive sheave and locking the system in place. So, the next time you step into an elevator and feel that tiny vibration or hear the hum of the machinery, don't see it as a sign of weakness. Don't picture yourself dangling by a thread instead. Realize that you are standing inside one of the most redundant and fail-safe machines ever built. You are surrounded by a symphony of electromagnetic interlocks, centrifugal governors, and steel wedges that are just waiting for a reason to bite. The modern elevator isn't a box fighting a constant battle against gravity. It's a masterpiece of friction that has made gravity almost irrelevant. We didn't just build taller buildings. We engineered a world where down is always a choice and never an accident. If you found this interesting, consider subscribing for more deep dives into the hidden engineering that shapes our world.